All right, chapter 7. So this chapter focuses on what they call non-conditional statements. And we've seen a few of these, like square root of 2 is irrational. Okay, it's technically non-conditional. It wasn't an if-then, right? So we're going to look at stuff like that. So we're going to start with biconditional, because this is the most similar to what we've been doing. So biconditional statements. If you remember, the biconditional was that if and only if thing, right? So the biconditional, that was P if and only if Q, that meant what? Yeah, P implies Q and Q implies P. So this means for an if and only if statement, I have to do two proofs within it. Okay, I need to do P implies Q and Q implies P. All right. So let's look at an example of that. So example 1, this is a fact we've been using, but now we'll actually prove it. I just wanted to get to biconditionals first. That yes, if 2, and I have integers here, let's make it real numbers because it's true for real numbers. If 2 real numbers multiply to 0, then one of them 0, or vice versa. If one of them 0, they multiply to 0. Okay. Your favorite, right? Super obvious statement. How the heck do we prove it? Well, it's not going to be bad. So here we go. Proof. So in a biconditional proof, it can help your reader if you say which way you're proving first. So here's one way it's commonly notated, is to put an arrow like that. So this is telling me I'm doing the direction that goes from left to right. Now, personally, I don't want to start with xy equals 0 and jump to here because I don't see any steps in the middle for that. To me, it's like, what do you say? You say duh. So I'm going to try contrapositive. Okay. So I'm going to assume x is not 0 and y is not 0. All right, and my goal is to show that their product can't be 0. Here's how I'm going to do that. So then we have 3 possibilities. So case 1, x is greater than 0 and y is greater than 0. Well, if I multiply 2 positive things, what do I get? Positive thing. Okay. Case 2, let's make them both negative. X is less than 0. Y is less than 0. If I have 2 negative things and I multiply them, what do I get? Positive thing. What's my last case going to be? No. Yeah, one of each, right? Now use without loss of generality. Without loss of generality. X, let's make X positive and Y negative, it doesn't matter. Then X times Y is what? Negative, less than 0. So in all possible cases, XY does not equal 0. So we proved one direction by contrapositive. So that's the forward direction proven by contrapositive. Okay. Now we're going to do the backward direction. And this one, I'm going to do a direct proof. So I'm going to assume x equals 0 or y equals 0. And my goal is to get x times y equals 0. Well, this one is as easy as it seems, right? If x equals 0, then xy equals 0, because 0 times, I guess, a equals 0 for every a in the reals. Similarly, if y equals 0, xy equals 0. And at this point, we're done. We can add a final statement if we want, but as you get higher and higher in math, they typically will drop that off. But we can say, therefore, xy equals 0 if and only if x equals 0 or y equals 0. The 3 dots mean therefore, yes. All right. What questions do you have on that one? That's our first example of a biconditional proof.
When you do your second proof, the opposite way, or whatever your second way is going to be, can you stop after that, or you're going to have to put something?
So no, once you've done both directions, you can just stop. It's just adding something under it would be if you feel like, well, maybe my readers lost their way. I want to pull them back to what we just did. That's fine. But yeah, you can stop after the second direction's done if you want. All right. So let's look at the next example. And in this example, we're going to use that previous result, actually. So we're going to let x be a real number. We want to show x squared minus 1 equals 0 if and only if x equals -1 or x equals 1. You actually probably did this a million times in middle school or high school algebra, right? But we're going to actually prove it. So proof. Let x be an element of the real numbers. I guess we'll start, well, let's start with the backwards direction. Why not? It doesn't matter. We can start with whichever direction we want. So I'm going to assume x equals -1 or x equals 1. All right. What do I want to show? X squared minus 1 equals 0. So we can say if x equals -1, x squared minus 1 equals 1 minus 1 equals 0. If x equals 1, x squared minus 1 equals 1 minus 1 equals 0. Either way, we are guaranteed x squared minus 1 equals 0. All right. Now let's do the forward direction. I'm going to do this using a direct proof. So what do I assume? Yep. assume x squared minus 1 equals 0. All right. Then let's factor it. X minus 1 times x plus 1 equals 0. So by example 1, so example 1 was what we just did. We just showed if two things multiply to 0, one of them has to be 0, right? So by example 1, x minus 1 equals 0, or x plus 1 equals 0. But what's that mean? There you go. X equals 1 or x equals -1. So thus, x equals 1 or x equals -1. And again, it's okay to end the proof there. It's okay if you want to add a last sentence saying, hey, I showed the if and only if. Okay. Yep, what's up?
By example 1.
Yeah, so example 1, we showed that if I have a product that's 0, then one of the pieces was 0. So I was referencing that fact down here because I have a product that's 0, so one of the pieces must be 0. Yep. And as your math classes get more and more advanced, that's going to happen more and more often, right? You're going to do the work to prove this one thing. Your teacher will probably do this hard proof in class. Once you have that result, you can use it, right? You don't need to reprove that every time. You can just say, hey, by theorem 3.7 from class, blah, 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 you know, and just go. So, yeah.
For one side, one the other way. So when you do the other way, you can assume that even though.
So think of each direction as its own mini proof. So whatever I did in doing this direction is completely erased and gone when I go back to do the other direction. So you're not assuming what you're trying to prove because you're starting over on a new proof, which is assuming something different with a different goal. Yeah. Yep, yep. All right. Let's definitely do another one. So here's one. Let a be an integer. A is even if and only if a squared is congruent to 0 mod 4. We've actually kind of seen this, but now we're putting a bunch of results together here. So proof, let a be an integer. And that's the only thing that carries through for both directions. So let's do the forward direction first. Let's suppose a is even. Now, as I'm working through, I'm keeping in my head, keeping in mind that this is the same thing as saying 4 divides a squared minus 0. All right, so that's what I'm keeping in mind as I go. All right. So a is even. What's that mean? Yeah.
There's a K.
Thus, a equals 2k for some integer k. All right. My goal deals with a squared, so I'd better square that. So this means a squared equals 4k squared. Since k squared is an integer, 4 divides a squared. Thus, a squared is congruent to 0 mod 4. All right, so for the other direction, if you try a direct proof, it's a little tough. And I think this is where some of you have hit trouble in the past, right? Where you say, okay, so if 4 does divide a squared equals 4L. And then you say, well, I need to get down to A, right? And if you take square roots, you lose the fact that L is an integer. Okay, integers are not closed with respect to taking square roots. I definitely get non-integers when I take square roots. So a direct proof does not work here, okay? But if I'm gonna go backwards and I do contrapositive, so let's do the backwards direction. So I'm trying to prove if A squared is 0 mod 4, then A is even. What would the contrapositive have me assume? Suppose A is odd, and that gives me a much easier starting point, okay? So suppose A is odd. Then A equals 2K plus 1 for some integer K. Integer K. All right. Thus, A squared equals 4K squared plus 4K plus 1.
I've never pulled someone out so fast in my life other than math.
Yep, you're getting fast at square and odd numbers, I bet. All right, so I want to say that it's impossible for 4 to divide this, which intuitively we look at it and go, duh, okay? But a nice way to say it, a clean way would be to use contradiction. So let's, for contradiction, assume 4 divides A squared. Then there exists L in the integers with A squared equal to 4L. So 4L equals 4K squared plus 4K plus 1. So I just combine the two equations together. Let's get everything with a 4 on one side and the 1 on the other. So rearranging terms yields, so rearranging terms yields 4L minus 4K squared minus 4K equals 1. But this means divide everything by 4, what do we get? L minus K squared minus K equals 1/4 is an integer. And that's definitely not possible, right? That's definitely a contradiction.
So we get a contradiction. We could just, that's it. It's right there.
Yeah.
You see it.
Yeah. So like here, yeah, it's obvious. If you look back at some of our proofs from chapter 6, if the contradiction is a little less obvious, I'll add a sentence, saying, but, A was supposed to be even or something like that before putting the contradiction symbol. Yeah. In a formal math paper, they wouldn't even put the symbol. They would literally write out, but this is not possible, or but this is a contradiction, something like that. Yeah. I think the book probably does it more like that. Yeah. All right. So this means this, there's a contradiction. Thus, 4 does not divide A squared, meaning A squared is not congruent to 0, mod 4. And I'll go ahead and put my box. If I had more space, this one, I probably would add an extra line saying, so by contraposition, if a squared is congruent to 0 mod 4, a is even, but technically we don't need it. Mhm. Yeah, so you could have argued that way that, yeah, so I guess that would have been the direct way. If you start with a squared 0 mod 4, a squared equals 4l. So if a were odd, then a squared should be odd, so a must be even. Absolutely. Yep, you could have argued that way. Other questions? Liz? All right, yeah, go ahead.
So since they are, each of the mini proofs are their own mini proofs, you can use the variable k.
Yes, each mini proof, since it is its own separate proof, I can reuse variables. The only variable that means the same thing in both is that a that was anything introduced before I start the two directions. That's set at the beginning. But yeah, anything introduced in a direction, you can reuse for the next direction because we're starting over from scratch. Yep. All right. So you'll notice I didn't leave much space for this little existence proof. Existence proofs are awesome when you can find the thing. So let me explain what I mean. So example 4, there exists an integer which has an irrational square root. Can you guys find a specific integer with an irrational square root? 2. We showed 2 was square root of 2 was irrational. So this proof is ridiculously easy. Proof. Note that 2 element is e, so 2 is an integer, and square root of 2 is irrational. Done. Put your box. So all it wanted, it claimed there exists an integer which has an irrational square root. And I said, yep, 2. Right? That's it. You only need one example. So good question. So depending on what, this is a pretty commonly known fact, so you normally wouldn't reference back. But yeah, if you are referencing back to something that is less commonly known, or you feel like, my audience is not going to be with me, yeah, you can definitely say, and by, example 5 from chapter 6 notes, square root of 2 is irrational, or whatever. It may have been example 1 actually. In chapter 6 notes, square root of 2 is irrational. Yeah, absolutely. That'd be fine. So that's the easiest type of existence proof, because if it says there exists, you just have to find one. So we said you can't prove by example in general, but if all they say is one exists, then yeah, you just need to find the one. Okay, so let's look at another. The integers have an additive identity. So then I wrote out in symbols what that means. It means there is some integer such that for any other integer, when I add them together, I always get that other integer. It never changes anything when adding. It lets it keep its identity when I add. So do you guys think you know what x would be? 0. So we're ready for our proof. Say, consider x equals 0. Since 0 plus a equals a, and a plus 0 equals a for all integers a, This X satisfies the desired property. Now notice this, we did not prove that 0 is the only thing that works, right? We just proved that something works because 0 happens to work. In this case, it turns out 0 is the only thing that works, but that would require something else, which we'll show after we do some more existence ones, okay? All right. Everybody okay with that one?
Why didn't you show?
Because it just said there exists something with this property. It didn't say there exists exactly one thing with this property. Yeah. So it's going back to the meaning of this backwards E symbol. Okay. That backwards E just means there exists at least one, right? Yeah. All right. Okay. So let's look at one that's a little different, but still the same idea. So it's saying for every integer, there is another integer such that their sum is 0. For every integer, there's another integer so that their sum is 0. Okay, well, notice the order these come in here. This for every n is declared first, so he can't be an example, right? He's arbitrary. So n is just n, but m has the there exists, so I can pick m. So if I want n plus m to equal 0, what am I going to pick m to be? Negative n. Okay, so here's our proof. All right. Let n be an element of the integers. Let's say consider m equal to negative n. Then I need to show two things. So it said there exists something in the integers that the sum is 0. So I need to show those two things. So why is negative n guaranteed an integer? Yeah, n is an integer, so his opposite, right, negative multiplying by -1 is still an integer. So the negative n is an element of z since n is an integer. Also, n plus m equals n plus negative n equals 0. Thus, we have the desired m. We can write it that way. All right, so everyone see how n had to stay arbitrary, but m, I was allowed to pick an example because m was that there exist, okay? All right, so I don't want you to think all existence proofs take like 1 or 2 lines. Okay, so we're gonna do one that has a little meat to it. This next one, you can see I left a lot of space for it and there's a reason. And I gave it a name because we're gonna reference it over and over and over after this. But it's going to use the idea of greatest common divisor. So let me remind you of what that means. Okay, so the GCD of two integers, it's the largest integer. So if it's the largest integer, that does mean it's going to end up being a natural number. Because if a negative thing works, then the positive version of it works. Okay, that is a factor of both. okay? All right. And then I put it in symbols. So GCD of AB is equal to D means that D divides into A, D divides into B, and if anything else divides into both of them, it can't be bigger than D, okay? That's what that says. D divides A, D divides B, and if anything else divides both, it can't be bigger than D. All right, so that's our definition. So here we go. Here's a cool fact that's super useful in like modern algebra and number theory. So if I have two natural numbers, we could change that to integers, but we'll keep it natural numbers. Then there exist two integers such that the GCD of A and B equals AK plus BL. That may look a little crazy, so let's just play with some numbers before we write up the proof. Make sure we understand what it's saying. So let's let A equal to B equal 3. What's their GCD? Ah, 1 is the GCD. 6 would be the least common multiple. So we want the greatest common divisor, so 1. So notice 1 does equal 2 times 1 plus 3 times -1. Nope, I got it backwards. 2 times -1 plus 3 times 1, right? Let's do one where it's not 1. So let's let A equal 4, B equals 6. Well, that's still too easy. A equal 4, B equal 14. What is their greatest common divisor? 2. Can I make a linear combination like this where I multiply 4 by something and 14 by something and get 2? 4 times -3 and 14 times 1. That's what we're wanting to prove here, is that no matter the situation, I can always make that happen. Okay. Do you guys have a feel then for the statement of this proposition, what it's saying? Okay. Okay, so
What do you mean by that?
I just mean this statement is saying that I can always find two integers where I can make this linear combination to get my GCD. Yeah, so I just wanted to do a few examples so we understood what the heck it was wanting us to do. Okay, but examples do not a proof make. So we're gonna have to do a little work for this one. Don't write too big. All right, we need to start with suppose A and B are natural numbers. Now, I'm going to have to do work to find the K and L that are going to make this work. All right. So this may seem a little strange how I go about this, but this is just comes from, well, this is a common proof nowadays, but the first person who came up with it just had to sit down and play with it till they found something that worked, right? So we are going to let capital S equal this set. So capital S is going to be a set. And it's going to be things of the form AX plus BY such that X and Y are integers. So basically I'm letting S be all possible linear combinations of A and B. All right. And I'm hoping one of those gives me the GCD because that's what I need to prove is that I get the GCD. All right. So in order to do that, I need to note that, here we go, A times 1 plus B times 0 equals A is an element of S. So S does not equal the empty set. Right, I'm guaranteed at least one thing in there, okay? Specifically, A is gonna be in there. Similarly, I could get B in there. I could do A times 0 plus B times 1. Okay, so I know it's not empty. I'm gonna need that fact in a second. What type of number was A? Natural number. So say also A is greater than 0. So S contains positive integers. It also contains negative integers, but we don't care about that fact. We just want the fact it contains positive ones, okay? All right, so if I have a set of a bunch of positive integers, like I have a set and it has, I don't know, 5, 7, 9, 24, 36, goes on forever. I can always guarantee there's a smallest in there, right? If they're positive. Rational numbers, that doesn't work, right? That was proof you had to do with the homework to turn in, but so rational numbers, that doesn't work. I can't guarantee a smallest, but with integers, I can guarantee there's a smallest one in there. Does that make sense if you think about it? That has a name, the least integer principle, the well ordering principle, all that. We'll get to those names later, but we're going to use that fact here. We'll get to those names when we look at induction, actually. Okay. So S contains positive integers. This means some positive integer is the smallest positive integer in S. Call it D. All right. Then, what's it mean to be an element of capital S? It means that you equal AX plus BY, right? For some integers, X and Y. So I'm going to say there exist S little s and T with D equal to AS plus BT. So this was all set up, okay? But here's my claim. D is actually the thing we want. That is actually the GCD of A and B, okay? So that's what we have left to prove. So we will show D equals the GCD of A and B. We don't have to put that sentence, but when you're doing a longer proof, it can sometimes help to cue your reader into where you're going so they don't lose track of what's going on in all the steps. Okay. So I want to show D is the GCD of A and B. GCD has two main things you need to show, right? It needs to divide both, and it needs to be the biggest thing that divides both. Okay, divide both and be the biggest thing that divides both. So let's work on the first part. So let's note that by the division algorithm, which we've seen, but I'll remind you what that is. By the division algorithm, there exist Q and R. Well, they would normally, we'd say integers, but A and D are positive, so we could say natural numbers such that A equals QD plus R. What the division algorithm says is that if I have two numbers, I can always do division and I could end up with remainder, right? So what this is saying is D goes into A Q many times with R left over. So we should add with 0 less than or equal to R less than D, okay? Because your remainder should be less than what you're dividing by, right? So if D is 5, I say, okay, I can get 25s into that with 3 left over. That's what the division algorithm says. We won't be able to prove that until we do induction. It's going to be probably the longest proof we do all semester, will be the division out proof that that's true. But that is true. Given any two integers, actually, I can always find the Q and R that do that. All right. So now we're going to be sneaky. So this means R equals A minus QD. But we know what D is. So let's plug in what D is. So we get A minus Q, AS plus BT. Now that, doing a bit of algebra, rearranges to A times 1 minus QS plus B times QT. Should it be a negative QT? It should, sorry. So I did some algebra and some substitution there. Does everyone see the steps? Okay, so we have R equal to this thing here, but wait, look at the form of that thing. It's A times an integer plus B times an integer. So that means R qualifies to be in capital S, because that capital S is everything of the form A times an integer plus B times an integer, right? So R qualifies to be in S. Here we go, but 0 is less than or equal to R is less than D, and D is the smallest positive integer in S. So we're going to get a conclusion from that. All right, so R is in S. R is between 0 and D. But D is the smallest positive integer in S. What's that mean about R? R has to be 0, yeah, because he can't be one of those positive numbers in there, or he would be the smallest thing in S, okay? So he has to be 0. So R equals 0. We're almost there. Hence, let's see, go back to the original, we get A equals QD, so D divides A. All right, so we got D divides A. We also need D divides B, but we could use this exact same setup, right? We would just start with B instead of A and then do the exact same steps. So B equals some Q prime D plus R prime and blah, 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 blah. So similarly, D divides B. What do you mean?
Like if something, if something, if we're going to do the same exact question, something else would be similar.
Correct. Yeah, if it's the exact same process for something else, you absolutely can say similarly.
Like specify that R and like D, S and T and stuff like that, specify like that they're integers and natural numbers.
Oh yeah, you're right. So I should have done that because it's specified up here what the linear combination should be, but you're right. I should have put that in here. So let me change colors so you guys can see it. So there exists S and T in the integers because I'm using the definition of S to get those. Yep. Oops. Okay. Thank you. All right, so we showed D divides A and D divides B, thus D is a common divisor. Of A and B. What's left to show? That it's the biggest common divisor. It's the greatest, right? We showed it's a common divisor. Now we need to show it's the biggest. So that means we need to assume we have, well, okay. So what we're going to show is that it equals the GCD basically. So it does divide both. It is a common divisor. All right. So let's say, note that by definition, GCD of AB divides A and GCD of AB divides B. This means there exist, we haven't used M and N yet, so there exist M and N in the integers with A equal to GCD of AB times M and B equal to GCD of AB times N. All right. Everybody okay with that, right? Every number is its GCD times some integer. Okay, the GCD of the two times some integer. So let's go back to our equation. D equals AS plus BT. This means G or D equals the GCD of AB times MS plus the GCD of AB times NT. So I'm going to factor out that GCD. All right. scroll up. Everybody with me so far? Okay. So what does that mean about the GCD in comparison to D? Which one divides which according to this? The GCD divides D, right? Because GCD times some integer gives me D. D is a multiple of the GCD. Thus, GCD of AB divides D. So they're both positive. They're both positive. So that means D is greater than or equal to the GCD, right? If they're both positive and one divides the other, the one dividing into something can't be bigger, okay? But DE is a common divisor. So if he's a common divisor and he's greater than or equal to the GCD, he must be the greatest common divisor, okay? Because we just showed he can't be smaller than the greatest common divisor. So, meaning D equals the GCD of AB. Therefore, I'm going all the way back to the problem statement now. There exist K and L in the integers. And we can say here, namely, S and T, because those are what we used, with the GCD of AB equal to AK plus BL. Hopefully you wrote small enough.
Is this the second longest proof in the semester?
I don't know. I don't know if it's the second longest proof we'll have, but it's up there. Yes. The other proof, you'll see. We'll have a whole page for it. And still, when you get to upper level math, maybe not undergrad, but like grad school, I had one course. The entire semester was one proof. So that was an extreme. Okay, that's an extreme. But yeah, the entire semester was proving the prime number theorem without using complex numbers. It took a whole semester. So, yeah, I mean, it's a known thing. It just takes so long and you need so many lemmas and so much buildup and just, oh, now we need this fact, we need this fact, we need this fact. It was a whole textbook. Yeah. I mean, my dissertation, the proof, so the buildup took, like, I don't know, 10, 15 pages, and the rest was basically my proof that I did. So, which was probably 40 or so pages. So yeah, that's why you have to realize I can reuse this variable, because I'm done with this variable. You can't just keep bringing in new ones because you will run out of letters. But you can use Greek letters, Hebrew letters, all that stuff. Hebrew letters, yeah. So a Hebrew letter, this is really off, but it's cool. See if I can draw it. Aleph. So Aleph not actually has a special meaning in math. That's why I kind of remember that one. That's a terrible, but that's the best I can draw it. That's the first Hebrew letter, I think. Aleph. Yep. All right, so any questions on, let's see how long it was, that proof.
How about long? That was a point.
Yeah, and so that's a good point. Let's go over, now that we have all the details down, let's look at the big picture again. So I want the GCD to be a linear combination of A and B. So I started by taking all possible linear combinations and took a specific element from that set. the smallest positive element from that set. And then my whole goal was to show, yes, that's the GCD. Because if he's the GCD, then the GCD is of the right form. It's that linear combination I want. So then we had to show, first of all, it's a common divisor. And second of all, it's not smaller than the GCD. So that was everything we did. Okay. We had to show it was a common divisor. Then we had to show it's not smaller than the GCD, which means it has to be the greatest common divisor. Yeah.
Will something this hard be on our homework?
No, so good question. So when it comes to homework, typically you're going to get ones that don't take this many steps, or if they do take this many steps, it's broken into pieces. It's like, okay, show this. Okay, now show this. Okay, now show this. And especially when you get to like your 400 level math, oftentimes your teacher will break it down for you and say part A, part B, part C, and they end up forming together to be a whole proof of something. Yeah.
You can do that. If you come in, you can, like, do, like,
I mean, yeah, now you would combine them all, you know, if you were doing a formal proof in a paper, but yeah, I mean, all these long proofs, that's what it is, okay, now I'm thinking about this. Okay, now we're thinking about this. Okay, now we're thinking about this. And then it all forms together. Yeah. All right. That's probably a good stopping point. Let me just give you an idea of what's the last thing in this chapter. So the last thing we'll have to do will be to show that how to prove something's unique. So like we said earlier, 0 is an additive identity if it's the property we wanted. But to show it's the only thing that works would require an extra step. So we want to learn how to do that to show it's the only thing that works. So you'll notice our same guy is kind of coming back here. So we'll have another semi-long proof for this page to show that, yeah, that there's a unique thing such that, but we'll talk about that next time. Okay, so that's good.